Week 7, Density-Based Clustering with DBSCAN. Welcome to your introduction to DBSCAN clustering. You will learn: what is density-based clustering? Why DBSCAN is different from K-means? How to find groups in real-world data, even if groups are not circles. We will use the Mall Customers dataset to practice. Let us dive in. Running the cell now. First, we will download our data. We download the Mall Customers data so we can use it. We turn off warning messages. We import pandas, a popular library for working with tables. Import numpy as np. We set the random seed to 42 for reproducibility. We set the data source URL for the Mall Customers dataset. We load the data into a table called df. We check how many rows and columns we have. We quickly look at the first few rows. Running the cell now. Here, we are loading the Mall Customers dataset, which contains 200 rows and 5 key columns such as age, annual income, and spending score. Notice how the data is structured with customer demographics and behavior metrics. This setup is crucial as we prepare to apply DBSCAN for discovering dense clusters in multidimensional customer data. What do you notice in the first rows and columns? What is clustering? Clustering is finding groups of similar data points. Why do we do this? To discover patterns, for example, what types of customers shop here? To divide customers for marketing, product planning, or help guides. Clustering is a basic way to explore structure in data with no labels needed. Running the cell now. Let us explore the important columns before clustering. We take a look at the column names to find which ones we want to use. We summarize the age, annual income, and spending score columns to get a sense of their values. Running the cell now. This output shows a quick overview of key customer features, age, annual income, and spending score. Notice the wide ranges and varied distributions. Ages span from 18 to 70, incomes from $15K to $137K, and spending scores from 1 to 99, highlighting diverse customer profiles. This variety is exactly what clustering leverages to group similar customers based on these attributes. Notice the ranges. Which feature might be most important for finding groups? K-means versus DBSCAN. You may have heard of K-means. K-means forms round, equally sized clusters. But what if groups are messy? DBSCAN to the rescue. DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. It finds clusters of any shape, even with outliers. You do not need to pick the number of clusters first. Running the cell now. Let us make a simple scatter plot before clustering. We add a comment describing that this plot visualizes customers by their incomes and spending. We import the matplotlib library for creating plots. We create a scatter plot of annual income versus spending score, with some transparency. We label the x-axis to indicate it shows annual income in $1,000. We label the y-axis to indicate it shows the spending score from 1 to 100. We add a title to describe what the plot represents. We display the plot on the screen. Running the cell now. This scatter plot shows how customers' annual incomes and spending scores are distributed, revealing visible groupings with varying densities and shapes. Notice that clusters, if any, are not perfectly round or equally sized, illustrating why K-means' assumption of spherical clusters might not capture the true structure well. This sets the stage for exploring DBSCAN, which can identify clusters of arbitrary shapes and sizes more effectively. Try to point at 2 dense clumps on the plot if you see them. What is density? In DBSCAN, density means areas where lots of points are close together. A cluster has many points in each other's neighborhoods. Points with few nearby neighbors may be called noise, outliers. DBSCAN needs two settings. EPS, how close points must be to consider as neighbors. Minute_samples, how many points needed to make a cluster. Running the cell now. Let us pick the columns we will use for DBSCAN. We only pick annual income and spending score as our features. This makes our clustering focus on financial behavior. Running the cell now. Here, we've extracted the key features, annual income and spending score, that will help us identify dense regions in the data. Notice how these columns represent the dimensions where DBSCAN will look for clusters with many nearby points, setting the stage to distinguish dense clusters from noise. This step is crucial for focusing the density-based clustering on the relevant attributes. Which two columns do you think would make sense to group customers? We must scale the values first. We use a standard scaler to make sure each feature has similar influence. Scaling means subtracting the mean and dividing by the standard deviation. If we do not scale, the feature with the biggest numbers can dominate the clustering. We fit the scaler and transform our income and spending columns. Running the cell now. This code standardizes the features by scaling them to have a mean of 0 and a standard deviation of 1. Although there's no visible output, this step is crucial because DBSCAN's concept of density relies on distance calculations, which work best when features are on the same scale. Standardizing ensures the neighborhoods DBSCAN forms reflect true closeness in the data. Why do you think scaling is important before clustering? Fitting DBSCAN. We will use scikit-learn's DBSCAN to find clusters. Let us start with some basic values for EPS and minute_samples. Experimentation is normal. DBSCAN gives different results if you tweak EPS. Running the cell now. Let us try clustering with DBSCAN. We import DBSCAN from scikit-learn. EPS is set to 0.5, how close points must be, and minute_samples is 5, the smallest cluster size. We fit the model and get cluster labels for each customer. We print how many customers are in each cluster. -1 means noise, outliers not in any group. Running the cell now. This output shows the count of points assigned to each cluster by DBSCAN, where 0 and 1 are the identified clusters and -1 represents noise or outliers. Notice that most points, 157, belong to the first cluster, while a smaller group, 35, forms the second, and only a few, 8, are labeled as noise. This confirms how the chosen EPS and minute_samples parameters influence cluster formation and outlier detection in DBSCAN. How many clusters did you see? How many noise points? Let us visualize what DBSCAN found. Start by preparing to plot the DBSCAN clustering results. Create a new figure with a size of 7 by 5 inches. Define a list of colors to represent different clusters. Loop through each unique cluster label found in labels. Use black for noise points labeled -1, otherwise pick a color based on the cluster number. Create a mask array for the samples that belong to the current cluster K. Plot the points belonging to this cluster using their annual income and spending score features, colored accordingly with some transparency. Set the label for the x-axis to annual income, $K. Set the label for the y-axis to spending score, 1 to 100. Give the plot a title to indicate these are DBSCAN clusters. Add a legend showing which color corresponds to which cluster or noise. Display the scatter plot on the screen. Running the cell now. This scatter plot visualizes the clusters found by DBSCAN using the annual income and spending score. Notice how points grouped by cluster color reveal dense areas of similar spending behavior, while black points indicate noise or outliers. This output helps us understand how DBSCAN groups data based on density with the chosen EPS and minute_samples parameters. Would you call these clusters useful? Why or why not? Let us try other EPS and minute_sample settings, and see how clusters change. This is a comment explaining that you can change parameters to explore more options. You prompt the user to enter a new value for EPS, which controls the radius for neighborhood points. You prompt the user to enter a new value for minute_samples, which defines the minimum number of points needed to form a cluster. You create a new DBSCAN object using the user-specified EPS and minute_samples values. You apply the DBSCAN clustering to the scaled data and get the cluster labels. You create a new figure for plotting with a size of 7 by 5 inches. You loop through each unique cluster label in the results. You assign black color to noise points, label -1, otherwise pick a color from the colors list cycling through it. You create a mask to select data points belonging to the current cluster. You plot the points of the current cluster on the scatter plot using annual income for x-axis and spending score for y-axis, coloring points appropriately and setting the label for clusters or noise. You label the x-axis as an annual income, $K. You label the y-axis as spending score, 1 to 100. You set the plot title to indicate these are the DBSCAN clusters from your settings. You include a legend to explain cluster colors and noise points in the plot. You show the completed plot with clusters and noise highlighted. Running the cell now. The output shows a scatter plot of clusters found by DBSCAN using your custom EPS and minute_samples values, with distinct colors for each cluster and black for noise points. Notice how changing these parameters affects the number and shape of clusters, illustrating DBSCAN sensitivity to density criteria. This visual feedback helps you intuitively tune the model for meaningful segmentation in the dataset. Try 3 settings. What happens if EPS is very small? What about very large? Subscribe to this channel for more practical data skills. Understanding DBSCAN labels. Each point gets a label like 0, 1, 2, or -1. -1 means the point is noise, it is not close to any cluster. Inspecting and counting cluster sizes helps you tell if your clustering worked. Running the cell now. Let us look inside each cluster for patterns. Get a summary of each group identified in the data. Import the NumPy library for numerical operations. Loop over each unique cluster label in the labels array. Create a Boolean mask for data points belonging to the current cluster K. Print the cluster number or noise if the label is -1, along with the count of points. Calculate and print the mean annual income for this cluster, rounded to 2 decimals. Calculate and print the mean spending score for this cluster, rounded to 2 decimals. Print a separator line to clearly separate cluster summaries. Running the cell now. This output summarizes the clusters identified by DBSCAN, showing that cluster 0 is the largest group with moderate income and spending scores, while cluster 1 is smaller but features higher income and spending. Notice that 8 points are labeled as noise, indicating they don't belong to any cluster. Their high average income but moderate score highlights why DBSCAN couldn't group them. This helps us understand how DBSCAN differentiates core groups from outliers based on density and proximity. Look at the means for each cluster. What do these values suggest? Let us compare DBSCAN to classic K-means clustering. This section compares the DBSCAN clustering method with K-means clustering. We import the K-means class from scikit-learn.cluster to use K-means clustering. We create an instance of K-means specifying 3 clusters and a random seed for reproducibility. We fit the K-means model to the scaled data and get cluster labels for each point. We set up a figure for plotting with specified size. We loop through each unique cluster label produced by K-means. For each cluster, we create a Boolean mask to filter data points belonging to that cluster. We plot the data points in the cluster using a scatter plot, coloring them uniquely and adding a label. The color for each cluster is chosen cyclically from the colors list. We label the x-axis as an annual income, $K. We label the y-axis as spending score, 1 to 100. We add a title to the plot indicating it shows K-means clustering results. We display a legend to differentiate between clusters. Finally, we show the plot with the clusters visualized. Running the cell now. This scatter plot shows clusters formed by K-means labeled 0, 1, and 2, each with distinct colors representing customer groups based on annual income and spending score. Notice how K-means assigns every point to a cluster, unlike DBSCAN, which can label some points as noise, -1. This visualization helps compare cluster assignments and highlights K-means' tendency to force all data into clusters, setting the stage to understand DBSCAN's noise detection advantage. Do you spot a difference? When might DBSCAN be better than K-means? Best practices for DBSCAN. Always scale your features first. Try several EPS and minute_samples values to get good results. Look at both the cluster plot and group summaries. Watch out for all noise or too large clusters, adjust settings if you see these. Remember, DBSCAN works best when clusters have dense, separate groups. Running the cell now. Here is how to check if your DBSCAN needs new settings. This section is for troubleshooting DBSCAN clustering results. Checks if all data points are considered noise by DBSCAN, labeled -1. Informs you that all points are noise and suggests increasing the EPS parameter. Checks if there is exactly one cluster and no noise points. Informs you that only one large cluster was found and suggests adjusting EPS or minute_samples. Covers all other cases that don't match the earlier conditions. Prints the number of clusters found, excluding noise, and the number of noise points. Running the cell now. This output shows that DBSCAN identified 2 meaningful clusters and flagged 8 points as noise, indicating a reasonably balanced clustering result. Notice how the code checks for extreme cases, like all noise or just one cluster, to guide you in adjusting EPS and minute_samples for better results. This aligns with best practices of tuning parameters and interpreting both clusters and noise to refine your model. If you get strange cluster sizes, what are 2 things to try adjusting? Here is an advanced way to guess a good EPS. Introducing a method to automatically find the best parameter using nearest neighbors. Import the nearest neighbors class from scikit-learn to find nearest neighbors of points. Create a nearest neighbors instance that will look for the 5 nearest neighbors of each point. Fit the neighbors model on the scale data x_scale to prepare for neighbor queries. Find the distances and indices of the 5 nearest neighbors for each point in x_scaled. Sort the distances to the 5th nearest neighbor for all points to observe the distribution. Plot the sorted 5th nearest neighbor distances to visualize the clustering structure. Add a title to the plot explaining it shows the k-distance graph used for estimating EPS. Label the x-axis to indicate points are sorted by their distance values. Label the y-axis to show these are the distances to each point's 5th nearest neighbor. Display the plot so we can visually inspect potential clustering boundaries. Running the cell now. This k-distance graph helps us visually estimate a good EPS value for DBSCAN by plotting the sorted distance to each point's 5th nearest neighbor. Look for a sharp knee or elbow in the curve. This indicates a threshold distance that separates dense clusters from noise. Using this approach aligns with best practices by providing a data-driven starting point for EPS, improving clustering results before fine-tuning further. Practice, locate the bending point on the chart and try EPS near that value. Mini-challenge, cluster customer types. Can you find parameter values for DBSCAN that give at least 2 clusters and less than 20% noise? Try different EPS values. Try different minute_samples. Look at the summary printout and plots. This is good practice for when you try DBSCAN on your own data. Running the cell now. Recap. Today you learned what DBSCAN is and why it is different than K-means. How to try, critique, and tune its clustering. That scaling data is important. Keep experimenting. Data mining is a skill you build with practice. Running the cell now. Thanks for learning. Rock it! If you enjoyed this lesson, please like, subscribe, and share. Try using DBSCAN on your own dataset and let us know your results in the comments below. Happy clustering, see you next time. Running the cell now.